Okay, it's good morning. So today's topic is something called work and something called energy. So energy and work are words that you've heard before, I'm sure, many times in your life. And sometimes people are referring to the physics definition, but most times you're just referring to the English normal definition. So work, you know, as what you have to do after school, when you do homework, what your parents go to do every day to their jobs, and many other examples of this thing called work. But in physics, work has a very specific definition, and there are things that are work and things that are not work. So that's what we're going to study today. So what is work? Work in physics is when you transfer energy to an object by applying a force to it and making it move. So it's basically the way in which energy is transferred to an object. Energy is transferred to an object by applying a force to it. By applying a force to it, which makes it move. So based on this definition, we can determine what is not work. So if work is when a force is applied to an object and the force makes it move, then we have three cases in which this doesn't apply. So the first thing that is not work is if the force is being applied but the object does not move. So force doesn't move the object. So an example of this could be if you have, let's say, a little block, as always, and it's just lying there. And there are two forces acting on this block. We know this pretty well by now. There's gravity, and there's normal force. So there are actually two forces acting on the block. But is there any work being done? No. There's no work being done because neither of these forces are making the object move. It's static there, it's not moving, so we say that no work is being done on the block, even though it has forces acting on it. Everything always has gravity acting on it. And gravity can generate work, but only when the object is moving because of gravity, so in free fall or things like that. So that's one case. If the force doesn't move the object, there is no work acting on the object. The second case would then be if there is no force acting on the object. No force. Well, that's moving it. No force acting on it moves it. So not because there are forces on it, is that it's moving. So it's moving, but not because any of the forces acting on it is doing that movement. So as we know also, if someone or something had pushed a block and it has no friction, it might continue moving for the rest of history, because there has to be a force stopping it. So if there's no friction, nothing will ever stop a block. So let's say this block is just moving and it'll forever move in this direction. So it's moving at, 5 meters per second forever. But again, the only forces acting on it are gravity and normal force. So it has a weight, of course, and it has a normal force, of course. Normal force, but neither of these forces are making it move. So even though it is moving, in this case it wasn't moving, in this one it is moving, but there is no force causing that motion. It is just moving forever. So in this case, there's no work. Again, there is no force doing work on the block. And the third one basically comes from the other two and is when there is no force in the direction of motion. So for a force to be moving the object, to be giving it its motion, the force has to have at least a component in that direction. So if all of the forces are perpendicular to the direction of motion, then there is no work. All forces are perpendicular to the direction of motion. So maybe, like in the classes before this one, we have an inclined plane. So the block can be moving downwards, right? So it's moving downwards with a certain speed. Yeah, and we have forces that have components in that direction. So we know that there is weight, and that weight has a component in that direction. So that parallel component of weight can be doing work. And we know that there could be friction, and friction is going to be doing a negative work because it's opposite to the direction of motion, but that's still work. Negative work is still work. But the force that won't be doing any work is normal force. Why? Because normal force is completely perpendicular to the direction of motion. So while the block is going parallel to the ramp, normal force is completely perpendicular to the ramp. So normal force is not causing any of the motion, or is not stopping the motion. It has nothing to do with that motion. So there is no work being done by normal force. So in this case, there is work being done by a component of the weight and by all of friction, but no work being done by normal force. So now that we know the three cases that are work, let's look at an example of that are not work. Let's look at an example of what is work. So let's see. Now we have a block, and this block is being pulled by a force. So let's do our free body diagram, as always, very important. So we have a weight. Let's say the weight is 90 newtons. We have a normal force. Let's say the normal force is also 90 newtons because there is no movement in the vertical direction. And we have a pulling force. So our pulling force, let's say, is 50 newtons. Those are all the forces acting on the object. And the object, as you guys can probably tell by now, is going to move to the right because there is a pulling force. So it's going to move to the right because there's no friction. So all of the pulling force is going to be used to move the object. So the object is going to move, and after some time, the object, which was here, is going to be over here. So let's say after it moves, it's going to be over here, the same block, right? And there's a distance from here to here of, let's say, 2 meters, right? So now we're going to get to the equation for work. It's actually a very simple equation. The equation for work is the following. Work equals force times distance. That's it. So F is force, D is distance. You can also use X, but so that you know that it's distance in any direction. It can be in X and Y and diagonal like here. And W, of course, is work. Right? So the equation for work is force times distance. In this equation, the only force that was doing work is the pulling force. So we don't take into account normal force and we don't take into account gravity. So our force is 50. So let's do this example. So we have that our work is going to be 50 newtons times the distance. So in this example, the object moved a distance of 2 meters. So that's what we put in the equation, 2 meters. So what's 50 times 2? 100. So our work done, the total work done by the pulling force is 100, and the unit is newtons times meters. So this is a very simple equation, just force times distance. That's what you need to remember. That's the equation. But if we have an example in which we need to find components, we need to use cosine, like we did when we were working with force in 2 dimensions. So let me change a little bit this example, just a little bit. So the pulling force is like one of the examples that we saw two classes ago, I think, in which the pulling force is at an angle. So we do have a pulling force, and let's say the pulling force is still 50 newtons. So the person is pulling with the same force, with the same strength, but instead of pulling parallel to the ground, he's pulling a little bit upwards. So actually, let's say there's the angle here is 20 degrees, right? So we need to do force times distance, but we don't care about the force, the net force in general, the total force, the magnitude. We care only about the component that is in the direction of motion. So we only care about this component of the force, the horizontal component. So we care about F pull horizontal, which I'm going to put an H. Yeah, so we had a vertical one, but we have a horizontal, and we only care about the horizontal. In that case, we need to use cosine. This component, the horizontal component, is cosine. I hope you remember that. So our equation now is going to be that work is F pull times cosine of theta. So F cos theta times the distance. Yeah, so it just depends. If there's an angle between the force and the direction of motion, you use this one. If there is no angle between the force and the direction of motion, you use this one. Although you can always use this one, and if there's no angle, you put a 0 here and you'll get the same result. But I find it easier to have 2 separate equations. So in this new example, we would do that the work is 50 times cosine of 20 degrees times, and this is newtons, times the 2 meters. So this is going to give us, let's see, cosine 20 times 2 gives us 93.97. So, a second, 93.97 newtons times meters. So notice that the work is a little bit less, not much, but a little bit less than when the whole force was doing work, because now only part of the force, a component of the force is going to be doing work, and the other component, which is perpendicular, is not going to be doing work at all. So that is work. And the last thing that I'm going to talk about is the unit of work, and then we'll be done with work. So let me erase here. So we saw in these 2 examples that when we do the multiplication, we get a unit of newtons times meters, because we're multiplying newtons and meters. So our unit is basically newtons times meters. But because we're talking about work and we're talking about energy, and this is used so much in physics, physicists invented a new name for this unit. So this thing right here is given the name joules, or joule, 1 joule, 2 joules, and the letter J. So from now on, we're going to use J for everything that's energy and everything that's work. So here we can change Newton times meter with a J, so it's 100 joules, and here too. 93.97 Newton times meter is 93.97 joules. So that's it for work.